All right, let's jump right into this explainer. Today, we're stepping onto the flight deck to completely master the Bombardier Q400 engine indication systems. We're going to take all that abstract engine data and map it directly to what you'll see in the hot seat, giving you a totally practical understanding of exactly how this aircraft communicates with you. To keep things moving, we'll scan the cockpit top to bottom. We're looking at the display's control panel, engine display core parameters, enunciations and system tests, secondary engine parameters, priority power plant messages, and finally, engine start and control. Let's get right into it. Section 1. The display's control panel. We'll start at the very top of our visual flow with the Engine and System Integrated Displays Control Panel. So, looking at the ESCP, the logic is honestly super straightforward. You push the ENG Sys button once, and boom, it momentarily brings up the engine system page on the upper area of the MFD when it's set to Sys. But if you push it a second time, literally nothing happens. So just remember the golden rule here. One and done. One push brings it up, the second push does absolutely nothing. Section 2. Engine Display Core Parameters. Moving down to the actual engine display, let's decode your primary thrust and propeller metrics. Check out the torque bug, marked right there in cyan. This little guy shows you the FADIC available torque, and it actually disappears entirely if the data is invalid or if you've got the condition lever set to start, feather, or fuel off. Now, the torque dial itself has green, yellow, red, and white arcs, and it goes completely white if the data drops out. The white torque needle swings into the yellow or red arcs depending on performance, parking at the maximum white arc value. But here is the crucial bit. It has a built-in 3-second delay before turning yellow. Why? Well, to prevent annoying false alarms during quick transient changes. The digital value ranges from 0 to 199% in 1% increments, matching the needle colors perfectly. So, your memory trick here? 3 seconds to yellow. The needle always waits before crying caution. All right, next up is the propeller RPM, or NP. The dial scale uses 6 colored arcs: white, green, yellow, red, and another white. And just like torque, it reverts to all white if the data is invalid. The white NP needle also turns yellow with that exact same 3-second delay we just talked about, or red in the corresponding arcs. Now for the digital value, it ranges from 0 to 1990 RPM. But notice how it jumps in precise 10 RPM increments? To lock that in your brain, just think 10 for NP. Those digital values will always jump in neat increments of 10. Now, when you're monitoring the ITT dial, you're going to spot a very specific red triangle popping up at 920 degrees Celsius. This marks your maximum transient limit, but here's the catch. It's only visible during an engine start and for exactly 30 seconds afterward. The needle turns red if you exceed this limit during a start or if you exceed the standard red line any other time. The digital readout shows -99 all the way up to 1999 degrees Celsius in highly precise 1-degree increments. Your rule of thumb for this one? 920 is for the start show. That 920-degree triangle only shows up for starts, plus those extra 30 seconds. Okay, let's look at your engine rating mode and bleed status. That green rating mode adapts to show NTOP, MTOP, MCP, MCL, MCR, or RDC top, all based on what you're doing with your condition levers, bleed selections, and panel buttons. The torque bug digital value stays cyan, reading from 0 to 199%. Now, if FADIC sets MTOP or NTOP, your bleed status pops up right below the rating. The word bleed shows in white for min and yellow for norm or max. And remember, selecting norm or max automatically forces an MCP rating if NTOP was originally selected. A super easy way to remember this? Min is white, max is yellow. Min has a W, max has a Y. Wait, actually scratch that. Just think W for min and Y for max. Simple. Section 3, Enunciations and System Tests. So this next part is pretty fascinating. Let's explore how the MFD visually signals active tests and display logic conflicts. Focusing in on the NH dial, it features 4 arcs and, you guessed it, reverts to white if invalid, with the needle simply turning red if you push it over the limit. But look closely at the digital value here. It reads 0 to 199.9%. What's really unique is that NH is the only parameter on this entire screen measuring down to a tiny 0.1% increment. Also, when you launch them, you'll see white OSG test or AF test messages appear, followed by in prog in white, abort or failed in yellow, or a nice green passed. To remember this specific detail, just think of its 0.1 precision. It's the most precise dial on the board.
The alerting logic here is totally built around catching your eye. When the FETIC requests increased power, a white UP trim message flashes in reverse video for exactly 5 seconds. Similarly, a yellow check ED message flashes for 5 seconds, then goes steady if the system spots a display discrepancy on critical parameters like torque, NH, NP, or ITT. We've also got the white AF select that appears when the button is pushed, changing to AF arm in reverse video for 2 seconds once both propellers are armed. What's your takeaway here? Flash for 5. Both the UP trim and check ED alerts give you a very deliberate 5-second visual wake-up call.
Section 4, Secondary Engine Parameters. Continuing our visual flow down the screen, we arrive at the secondary parameters. These are absolutely vital for your engine health monitoring.
Checking our health monitors, the NL digital value reads all the way up to 199% in 1% increments, displaying white normally and flashing red if it's over the limit. But I really want you to take a close look at the oil temperature dial. It is highly specific, literally cut up into 7 distinct colored arcs, including a red radial just for minimum starting. The needle turns yellow with a quick 1-second delay or goes straight to red, while the digital value reads from -99 to 199 degrees Celsius. So whenever you look at this complex dial, just think of the 7 slices of oil. Right next to that, oil pressure is measured digitally from 0 to 299 psi. The needle turns yellow with a 1-second delay, or red, and the dial has 5 arcs, with warning lamps triggering between 44 and 50 psi. But you know what's really brilliant about this dial? It actually uses 3 completely distinct scale factors: below 40, intermediate, and above 80. It artificially stretches the scales so that your normal operating pressure always sits optimally right between the 2 and 3 o'clock positions. It's designed that way so you can just quickly glance at it. Just remember, 2 to 3 is the place to be. Section 5, Priority Power Plant Messages. Moving on to a critical safety feature, we absolutely need to understand how the system alerts you when FADEC communication is compromised. So when FADEC communication drops or gets compromised, messages are displayed by decreasing priority right there on the center bottom line of the MFD. A white power plant message appears for a FADEC no dispatch annunciation. But, and this is key, if a single FADEC channel transmission fails, the system actually waits to confirm it before sounding the alarm. It takes a full 10 seconds of confirmed failure before that FADEC message pops up on your screen. That is your 10 seconds to fail rule. Section 6, Engine Start and Control. Okay, let's step away from the screens and move down to the physical control panels to see how our manual inputs actually shape the digital indications we've just studied. Down on the ice protection panel, hitting the intake door switch light opens the bypass door, which lights up the amber OPN segment. But the amber heater segment, that only comes on automatically if 3 very strict conditions are met. The bypass door has to be open, the skin temperature must be below plus 15 degrees Celsius, and the engines have to be running with AC power available. Pushing it again simply closes the door and turns the heater right off. So, cold, running, and AC, those are your 3 essential triggers to get that heater glowing. Swinging over to the engine start control panel, you'll see the ignition switch. Putting it in off disables ignition entirely, which is exactly what you need for dry motoring. In norm, the FADEC automatically activates the ignition during starts and, importantly, commands it on for flameouts and surges. The start switch light shows an amber select when armed and an amber start when initialized. The 3-position select switch arms your engines for start. What I love about this is the mechanical unlatching the very moment NH reaches exactly 50% on start. That switch mechanically snaps back to the center all on its own. So just remember, 50 frees the latch. Down on the engine control panel, we've got MTOP for max takeoff power and RDC NP LDG to reduce your RPMs to 850 for landing. Though keep in mind, this cancels itself if the condition levers aren't set to max within 15 seconds or if the power levers hit 65 degrees. We also have MCL, which changes the min rating to max climb at 900 RPM. But honestly, the event marker button is the most interesting one here. It saves your engine monitoring system data. Specifically, it records exactly 2 minutes prior to the moment you push the button and 1 minute right after. Think of it as a little time machine, 2 before, 1 after. Lastly, take a look at the RDC TOP, TR, Q, Reset, DEC, and MCR buttons. The Reset button restores your normal takeoff power, while the MCR button changes the 900 rating to a maximum cruise rating at 850 RPM. But the DEC button, That one is fascinating. It lets you reduce requested NTOP power in very precise 2% steps, capping out at a maximum reduction of 10%. Your rule to remember here is 2 to 10. You're dropping power 2% at a time up to a max of 10%.
And there you have it, a complete visual loop from your manual panel inputs all the way up to those primary digital displays. But honestly, it leaves us with a pretty provocative question to ponder. After mastering how to input these commands and read these parameters, how does the FADEC actually get under the hood to compute and transform those physical button presses into safe, precisely calculated engine thrust on your very next departure? Think about that incredible invisible translation layer the next time you're sitting in the flight deck. Thanks for tuning into this explainer, and we'll catch you on the next one.